So here you go. Yes. All right, so let's look at this. We're going to talk about a density curve that's not the normal distribution, and this problem describes one like that. It says a certain density curve looks like an inverted letter V. The first segment goes from, so let's draw an axis here, goes from the point 0, 0.6, so over here is the point 0, 0.6, to 0.5, 1.4, so that would be up here somewhere. And then from 1.5, 1.4 down to the point 1, 0.6. Okay, so here's what this curve looks like. The first thing you're supposed to do is sketch it. So they tell us that there are line segments connecting these things, so that's a reasonable sketch of the density curve. Some of you might want to put like maybe a dotted line here to indicate that it just sort of ends there. All right, first thing we're supposed to do is verify that this is a density curve. So we have two things we need to check. One, is it always above the x-axis? And then secondly, that the area under the curve should be 1. Is verify that the area under this curve is 1. So we can do that by probably breaking it into shapes that we know. You may decide to break it into two trapezoids, or maybe, let's say we make it a triangle and then a rectangle down below. That's probably the easier way to do it. So if we treat it this way, we have a rectangle on the base here whose height is 0.6 and whose length is 1. So that area is equal to 0.6 times 1, or 0.6. Then up above, we have a triangle. Okay. Now, we happen to know the base of that triangle is 1. And if we're careful, we even know how tall it is. Okay. And the way to think about this, this whole base of the triangle is located on the line y equals 0.6. You might say, how do I know that? Well, look at the two y values. That's 0.6 and that's 0.6. And this line just goes straight between them. So that's sort of your bottom y value. Your top y value is up here at 1.4. So what do we know? We know that the height of the triangle, which is out here, is 0.8. From 0.6 to 1.4 is the distance of 0.8. So I can write that in here. And then now we're ready. We get the height of the, well, we can use the area formula, that is. Area is going to be 1/2 the base of 1 times the height of 0.8, which is 0.4. That's what I was kind of hoping for, because when I add 0.4 for the height of the area of the triangle plus 0.6, which is the area of that rectangular base, I get 1, which is what I was expecting. The next thing we're asked to do is determine the median. And we discussed that the median is the equal areas point. So we're looking for a point on the x-axis such that if we draw a vertical line up, it'll split the area into two equal parts, equaling 0.5. And that happens right here at x equals 0.5. So if x equals 0.5, the area to the left of that point, all of this area, and all of that area is 0.5. So this 0.5 is the median. Okay. And then we're supposed to sort of sketch where we think the Q1 and Q3 might be. So to do that, let's just draw a new curve. So that's what it looks like. Here's 0.5 in the middle. Okay. And the thing we need to be careful about is where we think Q1 would be. We know it's the 25th percentile, but you can't be sure. Well, you can be sure of this. It's not here. It's not at 0.25. And the reason you know that is if you draw a vertical line up, and then you look at the area on either side of this. If you look at this area here on the left, compared to this area on the right, that area on the right is bigger. So this cannot be the median. So you're going to pick a reasonable place for the median. We know we need this green area to get smaller while the red area gets bigger. The only way to do that is to move slightly to the right. So maybe over here. So that's probably where Q1 is. And then the same reasoning would tell you that Q3, if you think 0.75 is here on the x-axis, there's 1, then you would think Q3 has to be closer to the middle a little bit, because this picture is symmetric. So that's where the quartiles are. So the next question we're asked to do is find the percent of observations that lie below 0.3. So we had marked off the median in the middle before. Here's 0.5. 0.3. All right, so what we're going to do is we're going to mark off 0.3 on the x-axis. We're going to trace that point up. And here we go. And if we want the area to the left, there we are. Now I could ask for this area in many ways. I could say, what's the probability that x is less than or equal to 0.3? I could say, what proportion of observations are 0.3 or less? I could say, what's the area of the density curve less than or equal to x equals 0.3? All of these things are synonymous ways of asking for that area. And this is just the area of a trapezoid. So we actually know some things about it. If we just trace around it for a minute, there it is. If we were to take that out of the picture, like maybe just imagine picking it up and putting it down over here. Here's all that area in the middle. Okay? So what do we know? How tall is it? Well, if you look here, that's the height of the trapezoid, which goes over here, which is 0.3. Okay? And we have two bases. You have an upper base and a lower base. That's always the case with the trapezoid. If you remember your formula is that area equals 1/2 times base 1 plus base 2 times the height. That's one way to write it. Okay, well, we know that this top base here is the same as the piece that runs along the x-axis, so that's 0.6. And then the only thing we don't know is the height of that one. Okay, so here's a way to do that. Maybe there's another way you might like better. But we want to get the height of that point. So my claim is if we could find the equation of this line, we could just sub in x equals 0.3, and we would know how tall it is. Here we go. The equation of this line requires we know the slope first. So I'm going to do m, or for slope, is change y over change in x, or 1.4 right there, minus 0.6 over here. And on the bottom, I'm going to have 0.5 minus 0. If we do that, we'll get 0.8 over 0.5, or 8/5. Okay? Now, we're lucky in this case. And the reason I say that is because we know the y-intercept is 0.6. There it is. So we can just write our equation right away. Y equals 8/5 of x plus 0.6. Okay. So if we take x equals 0.3 now and sub it into that equation, we get y equals 8/5 times 0.3 plus 0.6. And when you said y is what? What did you say it was? 1.083 approximately. Okay, great. So now that can go on the base of our trapezoid, and we're ready to find our area. So area equals, for that in a minute. All right, so one correction. I just realized this should have been 1.08, not 0.83. Okay, and we're ready. So the area is going to be 1/2 the sum of the bases, 0.6 plus 1.08 times 0.3, which is approximately 0.0972. I have to tell you, I'm a little bit surprised by that. And here's why. That's really low. And I know this is beyond Q1. So this is actually, I'm going to leave this error on the video. I'm not going to edit this out because I want people to, we knew that Q1 was bigger than 0.25, right? But 0.3 is not a lot bigger than 0.25, so I wouldn't expect that area to be so small. So let's just check our calculation. All right, so now the corrected answer is about 0.252. And that's sort of fun to think about because that confirms what we said earlier. We thought that Q1 would have to be bigger than x equals 0.25, right? We reasoned that out a moment ago. 0.25 is right here, and we said that the area to the left of that is probably less than 25%. And it turns out we need to go all the way to x equals 0.3 in order to get 25% of the area, or catch Q1. So the last part of this question asks us to do the following. Find the probability that 0.3 is less than our x value, and that our x value is also less than 0.7. So we can shade in that area pretty quickly. So here's where probably 0.3 is. Here's where 0.7 is. And that's the area we really want. Okay. And we have two options. One we could do is we could attempt to take this blue shape, break it into a triangle and a rectangle. We're going to have to find some y values. We'd have to know what that height is. We'd expect that height to be the same because of symmetry. And if you didn't know that, then you would unfortunately have to go find the equation of this line as well as that line. Well, we already know that first one. Plug both of these x values in, get the y values, find the equations, add two trapezoids together or whatever. But you have an advantage, and the advantage you have is that you know something from the previous problem. Anyway, we're going to avoid some of those complicated steps because we just learned something in the previous problem. We learned that this area here was 0.252. We also know we have a symmetric distribution. So we can say that this area out here is also 0.252. And because of that, we can get an answer pretty quickly. We know the answer has to equal the total area of the curve of 1 minus 0.252 minus 0.252. Or 0.496. So take advantage of symmetry while you can. I've been trying to encourage you to do this with the normal distributions, but it works in any symmetric distribution.